Hello everyone and welcome to chapter 5. In this chapter we are going to take pretty much everything that we've learned from the last 3 chapters concerning kinematics, and we need to ask the question, why is any of this stuff moving around? Because we have, as we already know, 5 different equations from the kinematics of different combinations of terms. I'm just going to write out a couple of these here. And we already know that objects can move around in 1 dimension, 2 dimensions, etc. We have all of our vector components that we can assign to these terms, but even though we can technically describe the motion of these objects using these mathematical expressions, we still don't have a reason as to why any of these things are moving. What's going to cause this block to accelerate to the right? What's going to cause it to change its velocity? What's going to cause it to move throughout a given displacement? And so that's what the next part of the class is focused on. And that something which is causing all of this to happen is what we're going to call force. And force relates directly to another term which we have not yet seen in any of our problems, whether they're homework problems or quiz problems. And that missing term is the mass of the object. You'll notice with all the previous work that we've done, whether it was a car or a planet or even just a small particle, the only thing that we've done is we've looked at these terms of velocity, displacement, acceleration, etc. But we've not yet addressed the fact that a car is much larger than a particle, and a planet is going to be much larger than a car. And so how do we get these objects of differing sizes and objects that carry considerably different amounts of physical matter, how do we get them moving? Well, we're going to use this term called force. And whenever we apply a force to a mass, that mass will begin to accelerate. And so we have the probably most famous and most basic of all the physics equations that are out there, F equals ma. And now we know that if we apply a force to a mass, that mass will begin to accelerate. And once we know the acceleration of a given object, we can take that information to learn about how the velocity of that object will behave and how the displacement of that object will behave. So here I'm going to write this displacement as delta r, because we are now considering 2 and 3D vectors. But this brings in another consideration for vectors. Keep in mind the equal sign here. Not only does that equal sign say that we have to have the same numerical values on each side, but it also says that we have to have the same vector directions on each side. And mass is going to be a scalar quantity. If you remember back to our definitions of vectors and scalars, vectors have to have a physical direction associated with them. Well, what direction does mass point? And if that doesn't sound like it makes sense, it's because it doesn't. And that's because mass is a scalar. Mass does not have a physical direction. And in our discussions on vectors, we learned that if we multiply a vector by a scalar, it does not change the direction of the original vector, it just changes the magnitude. And so whatever direction we have for our force, that is the direction that our object will begin to accelerate. So if we take a mass, if we take a block of mass m and we apply a force to it, we will then see that mass begin to accelerate in the same direction as that force. The rate of that acceleration will be based on the ratio of force to mass. And what this means is that we could apply the same force to two different masses. Call this mass 1 and mass 2. And the way I've drawn this, mass 1 looks considerably larger than mass 2. But we'll apply the same amount of force to each of these masses. Our expression says that F equals ma, and so we will see mass 1 begin to accelerate at a certain rate, and we will see mass 2 begin to accelerate at a certain rate. But this means that the acceleration of mass 1 is based off of the ratio of force to mass, and the acceleration of mass 2 is based on the ratio of force to mass. And so if mass 1 is much larger than mass 2, we are taking a force, oops, wanted that to be my highlighter. We are taking a force and we're dividing it by a much larger number, which means we're going to get an acceleration vector that is much smaller than what is produced for mass 2. So long story short, the smaller of the two masses can accelerate at a much higher rate because the force doesn't have as much material that it has to move. So it is possible to have the same force magnitude acting on two masses and get two completely different accelerations. But what would we have to do if we wanted these two differing masses to have the same accelerations? Well, in that case, let's take what we have for our acceleration expressions. If A1 is equal to F over M1 and A2 is equal to F over M2, we already know that M1 and M2 are not equal to each other. And if that's the case, if we keep the forces equal, there's no way that we can achieve this equality. The only way that we're going to be able to achieve an equality is if we have separate force values that are acting on each of these masses. And so in order to get these two ratios to truly equal each other, the large mass of mass 1 will need to be accelerated by a larger force, whereas the smaller mass of mass 2 will need to be accelerated by a smaller force, thereby maintaining a consistent ratio of the terms. All right, well, this equation that we're going to be using quite often F equals ma. This is actually a law of motion that Isaac Newton came up with while he was back home during the time that the colleges across the United Kingdom were closed down because of the Black Plague. And he actually came up with 3 laws of motion. This is just one of the 3. And so we're going to take a little bit of time to discuss what those 3 laws of motion are, because they are going to provide us the foundation of setting up the mathematical expressions that we use to describe how we're eventually going to get back to the acceleration of our object. And once we know the acceleration of our object, then we can go back and we can use those kinematic equations. So, the 3 laws of motion. Now, when it comes to a law, there are a number of different laws throughout math and science. You have like the first law of thermodynamics, second law of thermodynamics, etc. And what these are expressions that are meant to be got to think of the right word here, but absolute. They will apply to any given system. And that is not an easy thing to do, because in the real world, we are constantly being faced with exceptions to all of the different rules and theories that we have, which is why they're called theories. Those theories usually very well cover the majority of the situations, which is why we use them quite often. But every now and then you do run into an exception to the rule, and so the theory remains a theory. But if you can absolutely cover all of the possible conditions and still get them all to follow the rule and the statement that you've laid out, then it becomes a law. And so, given how difficult that is to pull off, now consider that Newton was able to do it 3 times. He came up with 3 laws on his own. And so the first of those 3 laws was actually around before Newton. It was just incorrect. And so Newton had to come along and correct it for everybody. And so I will write out the first law as it appeared before Newton, and then we'll talk about why it's wrong, and then we'll update it, we'll fix it so that it can actually become an actual law that will fit every situation. So this first law, this incorrect version, says that an object in motion will remain in motion as long as an outside force is applied to it. So that was the law, and this was basically how things were accepted for a number of centuries before Newton came along. And if we think about this, it actually does make a lot of sense. If you were to take a block of mass and sit it on a flat horizontal table and slide it across that table, well, you can apply a little bit of force over here to get it moving. But then once you get it moving, you remove that force, and what happens to the block? Well, eventually it slides and it comes to a stop. And so the only way that you could continue to keep that mass moving was if you continued applying that force to the block the entire time. Now, because that force was being applied, that would, in a sense, affect the velocity of that block. You would have to consider that block would not be slowing down, but it would constantly be speeding up. And so this made perfect sense to people. If you want something to move, you have to apply a force to it, and if you take the force away, it's going to stop. That was perfectly understood. And so Newton came along and he says, well, that's not entirely true. What if you removed the conditions of things like air resistance and friction? Because there will be some air resistance, air trying to flow around this mass as it's moving. There will be some friction between the mass and the tabletop. All of these things trying to slow it down. And these are technically outside forces, but those outside forces are not helping to keep the mass in motion. And so Newton said, well, let's consider that we have our mass and we place it into an environment where there is no air and no surfaces that it can come in contact with. So essentially, we would have to place this mass somewhere in outer space. And so now if we take that mass and we apply a force to it, that mass will start moving with some velocity. Then we remove the mass, but now as this mass travels through space, if there are no forces present to act on that mass, then let's see, zero force would have to equate to a zero acceleration. The other alternative would be to have a zero mass, but then we don't have an object. And so with zero acceleration comes the idea that velocity does not change. And if we have a initial velocity that is not equal to zero, remember we gave this this mass a little bit of initial velocity with that applied force. This means that I have a constant velocity, and as long as this mass does not encounter any additional outside forces, it will continue to travel forever and ever at that constant velocity. And so Newton said, well, we have to rewrite this. We have to update this for the correct situation. So that's what we're going to do. We're going to update this expression. But we have to be very specific with the wording, because if we want this to be a law that applies to all situations, the wording has to be specific. And right now, this wording here is kind of vague. It's almost too general, which is why it fails, because we were able to find a situation right here that disproves that statement. And that's all it takes is one example to disprove. You can have a million examples that agree with it, but it only takes one to disprove it. Alright, so I'll clear out this stuff here because I want to write the updated version right below it. So instead of saying an object in motion, can we be more specific about that? So an object in motion. Let's say, and I'll put a little asterisk here because this is our updated version. Let's say that an object with constant velocity. So technically that is an object that is in motion, but it's a specific kind of motion. We have a constant velocity. An object with constant velocity will remain at constant velocity as long as no outside forces act upon it. All right, so this is our first revision. We are going to go back and revise it again. So let's take this and we'll play around with this idea a little bit. So we'll take our mass and we'll put it out in space. We'll give it a little shove just so it has some initial velocity, and then we'll take that force away, and this mass should continue traveling along a straight line forever and ever and ever, as long as we don't act upon it with any kind of outside forces. Okay. So now we have to start getting a bit critical with how we interpret some of these terms. The term constant velocity. What does that mean? Well, constant velocity means that the acceleration has to equal 0. And 0 acceleration means that the velocity has to be constant. So let's consider a block that is sitting on a table. And as that block sits there, it's not moving. And so does the definition of constant velocity apply to this? And you'd say, well, it's not moving. Its velocity is 0, but is the velocity changing? And the answer is no. And so you have no change in velocity, which means that your velocity is constant. So 0 velocity can be used as a form of constant velocity. Almost kind of an oxymoron there. You have 0 velocity, constant velocity, but so we can say that there is constant velocity, which automatically implies that there is 0 acceleration acting upon this mass. So far we have everything covered, at least for the first line and a half of our revised statement. But now we have the second sentence that says this can happen as long as there are no outside forces acting on the mass. Well, remember, the law has to cover all situations. We can't just have everything happening up in outer space. Eventually we're going to have to come back down to Earth here. And on Earth, we do have accelerations, specifically the acceleration due to gravity. Gravity is always going to point down towards the ground. And if I combine the mass of this block with the acceleration due to gravity, then we produce what we call a gravity force. And so there is an outside force of gravity acting on this mass. And that force is not zero. That acceleration is not zero. So how can that mass have a zero acceleration? Well, the only way that that could happen was if there were another outside force that was canceling out the force of gravity. And there is. Turns out as the gravity force, also known as the weight, as the weight of this mass pushes down onto the tabletop, the tabletop has to push back with an equal and opposite counterforce. So we'll call this force counter. And now if we add the gravity force and the counterforce together, the net result is zero. We have two equal and opposite forces acting on the mass, but they cancel the effects of one another, and so we now have what is called a net force. And the definition of net force is going to be the summation of all forces that are acting on our mass. In this case, we just have these two right here, but they've added up to equal zero. If we apply the F equals ma expression to the idea of net force, then we get something called a net acceleration. And this net acceleration is what happens when all of the forces in the system get together and act on our mass. Except for this case, the net force has added up to zero. And so regardless of the mass, we get a net acceleration that is equal to zero. And well, now that fits in with what we're seeing. So it is true that if we have a mass that is just floating through space, traveling along with a constant velocity, minding its own business, if there are no outside forces to add up, then technically the net force would be zero, which means that the acceleration on this mass would be zero, which means that its change in velocity would be zero, which means it could maintain a constant velocity. But we can now see that we can achieve the same thing and still have outside forces acting on the mass. The condition is that those outside forces have to add together to produce a net outcome of zero. And so we'll come up here and we're going to modify this yet again. So I'll put an even bigger asterisk there. An object with constant velocity will remain at constant velocity as long as we've seen now that we don't have to completely eliminate all forces from the system. We just have to make sure that those forces are combining in a very specific way. So we'll say as long as the net force acting on the mass equals 0. And we now have our finalized version of the first law. Now the book will probably have slightly different wordage than this, but it's the same general idea. If we want to get something moving at a constant velocity, we have to maintain a net force of 0. And that's not to say that you can't have forces acting on your object. It's just that the combination of all those forces has to add up to 0. So that's our first law. That's our first law of motion. And we'll go ahead and surround this with some green so that we know that that's the real deal. And now we'll move on to the second law. Second law is really easy because we've already talked about it. F equals ma. That's it. That is our second law. And we kind of use the second law to help us in defining what the first law was. And there's nothing wrong with that. But I would always prefer not having some kind of circular argument here. But what we know is that if we apply a force to an object, it will start moving, and if we apply more force, it moves faster. And so this idea of F equals ma, this is going to be how we set up all of the equations that we're going to need to do our physics problems in the next, I'd say about 4 chapters. Because we are going to have masses with forces that are acting on them in all different directions. And every problem with forces could have a slightly different combination. And so trying to add up all of the forces for this first diagram would result in a net force that is different from the net force that we would get in this second diagram. And so there's unfortunately no equation that we can look up in the book that we can use to just solve our homework problems. We had that list of kinematic equations, and once we had those equations produced, well, then we could just go back to that list and we could choose the appropriate equation for the problem that we were doing. But now there are so many different possibilities as to how I can combine forces in a system that the number of possible equations is infinite. And we don't have the time to sit here listing out every possible combination of forces and angles. Instead, we're going to start right here. And we're going to look at each system independently and put those forces together in an equation that describes what's happening in that system, and then we'll use that equation to solve our physics problem. So if you go back to the 10-step problem solving process that we talked about, step 6 in that problem solving process said that we need to produce the equation needed to solve the problem. And that's what we did back in Chapter 2. We produced all of those kinematic equations and then we used them. Well, now we are going to have to produce the necessary force equations to solve the problems that we're going to be faced with in our future homeworks and exams. And so I realize how bad this sounds, but we are literally going to be making stuff up as we go. But it's going to follow the steps of the physics in how we make up these equations. So we're not just throwing things together, making up imaginary stuff. It's actually going to be founded in some logic and reasoning and mathematics. But that's our second law. It's just an equation. And so the third law, well, the third law we've already talked about as well. We just didn't know it. And the third law comes from this interaction right here. And you've probably heard the third law in some form or another. I'll go ahead and write it out the way that you've probably heard it, and then we'll update it for our purposes. For any action, there is an equal and opposite reaction. So something like that, I could say you push me, I'm going to push you back. There's an equal and opposite reaction there. But we need to apply this to a physics situation, specifically for the idea of force. And we can do that using the picture that we had up here. I'm going to go ahead and redraw it down here so that we can see it paired with our statement. So if I take our mass and I place it on the tabletop again, the weight or force of gravity will push that mass into the tabletop. Yet if our mass is not going to accelerate, the only way that can happen is if the net force acting on that mass is 0. And so this says that in addition to the weight, there has to be some other force in the system that is causing everything to add to 0. And we were calling that the counterforce. So force counter. Well, now if we take that and rearrange it algebraically, the counterforce would have to equal the negative amount of the gravity force. In other words, these two forces would have to have equal magnitudes, but they're pointing in opposite directions. So, equal and opposite reaction. Well, we're not going to use the word action and reaction. Action and reaction. Reaction sounds like we're in a chemistry class. We're not. So instead, we're going to use the term force. For any force, there is an equal and opposite counterforce. And again, that goes back to the idea. You push me, I push you back. Okay, well, now that we have this idea of force and counterforce, we want to start putting together a list of very specific types of forces that we are going to encounter time and time again. And these forces are special in their own right because they're going to behave in a very specific manner. And we need to know how these forces behave so that when we put everything together in our sum of forces expression, that we get the right outcome. Because ultimately we want to take all of these forces, however many forces there happen to be in a system. I'll just stop with 3 here. But if I have 3 forces acting on a mass, all those forces have to get together and they will determine how the mass accelerates. So all of these forces added together equal what we are calling the net force. And the net force determines how our mass will accelerate. Well, there's really no reason for having to write out this bottom line here. We can just say that all the forces in the system are going to get together and they're going to be responsible for accelerating our mass. The bigger question is, well, how are we going to add those forces together, especially if they're all pointing in different directions? Well, therein lies the vector notations that we've learned back in chapter 3. I don't want to attempt to add together multiple vectors that exist in 2 or 3 dimensions at the same time. I would much rather take this expression and break it up into x and y components. So whatever the net force is that acts on our mass, that net force should have an x component associated with it, and it should have a y component associated with it. If I know what those 2 components are, then I can put them back together and form the magnitude and direction of that net force. So how do I find those components? Well, that's where we're going to take the components of each individual force that we are adding together, and we'll add those together. But if the net force equals the mass times the acceleration, if the net force has x and y components, then shouldn't the net acceleration also have x and y components? And the answer is yes, it should. And so the combination of all of these x components of force are going to result in telling us how our mass will accelerate along the x direction. And then we can just kind of mirror everything that we've seen here for the y direction. If we want to know the y component of the net force, we are going to add up all the y components of our individual forces, and they will tell us how our mass accelerates along the y direction. And so this method of taking our individual forces and breaking them up into components and then treating the system as 2 one-dimensional problems is far easier and far, I would say, cleaner in terms of trying to keep track of everything. Because right now we can see that trying to zoom out here, it doesn't want to let me. But right now our choices are to do one two-dimensional problem or two one-dimensional problems. And at this point in the semester, we should be pretty proficient in breaking up vectors and performing one-dimensional mathematics. We can always take that information about the x and the y components and we can put it back together with Pythagorean theorem and inverse tangent and reproduce all of these vectors, but it is just so much easier to work with any vector system using its components. And so that's what we want to do as we go forward with all of these other vectors that we're going to define. So let's make a list of those special forces that we're going to be dealing with in the coming lectures. So these special forces, and I'm just going to list them out right now so that we have an idea as to what the next discussion topics are going to be. The first one that we're going to talk about is gravity. The next one is tension. And so tension is going to relate to forces that are transmitted through connections using ropes or chains. They can even be rigid bodies like a piece of rebar that can hold some tension force. And then we're going to have something that is called the normal force. We'll talk about that some more. And these will be the primary focus for this Chapter 5 material. And then we're going to segue into Chapter 6, where we start talking about friction forces, centripetal forces. And so if you remember from our Chapter 4 discussion, centripetal referred to the center-seeking centripetal acceleration. Well, that's an acceleration, and if you have an acceleration, there has to be a force. And so all we have to do is pair any acceleration term with a mass, and what we did one side, we have to do the other. And so now we have an expression that we call the centripetal force. So there's going to be some force that points towards the center of the circle, and that force is responsible for accelerating the mass towards the center of that circle. But even though we've got this definition in front of us right now, this in no way means that we've learned about centripetal force, because we actually have to take the time to identify what force is causing this to happen. And those culprits are going to come from the list of all of the other forces that we need to talk about. And then when we get into Chapter 7, we're going to consider variable forces. And so these are forces that are not constant. And if a force is not constant, that means that there's one of two possibilities as to why that force is not constant. Either the mass is not constant, so you're either gaining or losing mass somehow, and that can happen. A really good example of that would be like a rocket. As a rocket blasts off, it's constantly expelling mass in the form of fuel, and so it can have a variable force. But we're mainly going to focus on the idea that instead of having a variable mass, we want to keep the mass constant, and so we will have a variable force. And if you remember, one of the big conditions about using kinematics was that we had to have a constant acceleration in order for the calculus to work out and produce the equations that we were using for the kinematics. And so the kinematics will not always work in every conceivable situation, because sometimes you'll have a non-constant acceleration, and so we need to figure out how we're going to deal with that, but that's not going to happen until we get to chapter 7. But this just kind of gives us a roadmap as to what to expect for, I'd say, the next 6 to 8 video sessions. But let's see here. But we really do need to go through this list and provide some detail as to how each of these forces is going to act. And so let's see how we're doing on time. Just want to go back, see exactly what's been covered here. I think this would probably be a good time to end the video, even if this video is a little bit short, because it would be a lot more efficient if we could combine the definitions of these three into one video and then follow that up with some example problems using those 3 types of forces. So I think we'll go ahead and end the video here. We've got all the foundation information that we need. We're definitely going to be using all of these definitions for motion and force and what it takes to maintain constant acceleration. And so we'll pick this up at the next video. See you then.